The behavioral response of assistive and therapeutic exoskeletons to the user's actions ideally should be adaptable rather than fully pre-programmed to generate the required assistance as a function of both the capability of a user and the rehabilitation outcome. The main objective of Biomot project is to improve existing wearable robotic exoskeletons, proving more flexibility and seamless integration with the human motor control system. For this, we propose a neurorobotic framework for exploitation of dynamic sensory-motor interactions and developing cognitive capabilities, which can lead to symbiotic gait behavior in the interaction of humans with existing and future wearable robots. Biomot research requires the combination of multiple disciplines contributed by European institutions and a Japanese partner. Experimental analyses of human walking are conducted from clinical, neurophysiological, and biomechanical angles. These experiments set the basis for the development of detailed biomechanical models and bio-inspired solutions to implement control of physical interaction with the body. This control level is integrated with higher-level learning algorithms to derive symbiotic behavior. Biomot proposes an architecture to extend capabilities of wearable exoskeletons with intimate coupling with human neural and musculoskeletal structures. In the design of this architecture, we use biology as inspiration to emulate multiple levels of sensory information processing, self-regulation, and adaptability. The Biomot architecture allows researchers and developers to add layers according to enhance motor control recovery or to augment human performance. Thanks to this framework, Biomot exoskeleton can rely on mechanical and bioelectric measurements to adapt to a changing user or task condition and hence improving robotic interventions by enhancing motor adaptation.
The 3 joints of the Biomot exoskeleton are actuated by a variable stiffness actuator developed at the VUB. This actuator, called MAKEPA, can emulate the biomechanical properties of the human muscles. The MAKEPA spring can store and release energy, and this can be used in different phases of the gait cycle to have an energy-efficient actuation system for exoskeletons. The behavior of the actuator can be changed from more compliant to more stiff by changing the precompression of the spring. One of the main advantages of the MAKEPA is that it can be used as a torque source without having a torque sensor while being position controlled. The realization of the MAKEPA for the 3 joints of the Biomot exoskeleton is different, since the 3 joints have different requirements. For example, a spring working in parallel to the MAKEPA is added only at the knee joint. The actuators of the final prototype of the Biomot exoskeleton have high torque-to-weight ratios. They can indeed provide high torques while weighing only between 1.2 and 1.6 kilos.
In Biomot, we aim to create a symbiotic interaction between the exoskeleton and the user. Therefore, the exoskeleton needs to understand what the user is doing and how it is affected by the action of the exoskeleton itself. Of course, what the exoskeleton understands is numbers, and we give it these numbers by placing sensors on the user and processing the biological signals that we acquire. Unfortunately, there are no sensors that can give us direct measurement of human internal dynamics, so we need to collect indirect measurements and process them through a model. The sensors we use are electrodes, like these, that we place on the muscles of the user to measure the electrical activity that elicits muscle contraction. We also have sensors on the exoskeleton that measure the kinematics, that is, how the person is moving, and we can combine these 2 sources with a subject-specific musculoskeletal model that continuously estimates the state of each muscle. We are able to estimate the forces of the muscles, their stiffness, and how they overall contribute to motion generation. This information is used by the exoskeleton controller to adapt the level of assistance offered to the user, and also to understand how gait dynamics are affected by the presence of the exoskeleton itself.
When wearing an exoskeleton, there is a constant interaction between the patient and the robot at all times. Therefore, together with partners from Riken in Japan, we set to develop a control scheme that allows a mutual adaptation between them. Thanks to the Biomot actuators, we can easily measure the interaction forces at the joint level between the robot and the patient. This way, we can modify the behavior of the actuator to adapt to the patient's movement capabilities and guide the patient towards a more natural movement.
The cortical potential of the user during gait have been studied in the Biomot project. In order to do that, the cerebral activity is measured through a non-invasive cerebral interface. Several cognitive mechanisms have been studied to detect the attention level, the intention of starting and stopping the gait cycle, the reaction to unexpected obstacles, or studying the relation with cortical and muscular activity. This information allows obtaining a model of the mental state of the patients while using an exoskeleton. In the Biomot project, we have focused on measuring the patient attention level to walking. Our goal is to guarantee the patient involvement in rehabilitation tasks. For that, the measure of attention level will modify the control parameters of the Biomot exoskeleton. This way, the exoskeleton conveniently guides the patient to a desired movement pattern, while cognitive involvement is promoted.
In Biomot, we propose the use of detailed human models to monitor the patient and control exoskeletons. The neuromusculoskeletal model provides precise information about the forces that are produced by a human user during gait based on the muscular activation. Thus, we apply such estimates to inform the controller of the exoskeleton to act according to real measures of user capability, giving only the required support. This control approach, informed by embedded computational models, improves the state-of-the-art in exoskeletons while being able of evaluating muscle contribution to movement in healthy and pathological cases. For example, with Biomot we can control as needed the artificial robotic assistance to enhance propulsion during walking based on estimates of forces produced by human ankle muscles.
People with spinal cord injury will take enormous advantage of the possibilities offered by the technology developed in the Biomot project. One of them is the actual possibility of linking the mental state of the user related to the walking task to the exoskeleton actions, in a way that the involvement can be maximized, which at the end is behind the success of any rehabilitation therapy. On the same line, Biomot is able to accurately estimate user contribution to the movement, which allows to the therapist to accurately select the support to be provided by Biomot in order to maximize the outcome of the therapy, having into account a real-time estimation of the contribution of the user. In other words, Biomot offers the opportunity of tuning the therapy based on the actual effort and attention of the user, allowing to optimize the therapy and therefore the outcomes.